Morning. This is the video for the investigation number 1 of the graphs of polynomials unit. Alright, so today we're going to be investigating graphs of polynomial functions. So we're just going to be looking a little bit at what a polynomial looks like. We'll be working with terms and more solidified definitions in the next lesson. But for today, we're going to just be sketching graphs from pictures on our calculator. And 2 vocabulary words that we need to know for this lesson are degree. Degree is the highest exponent that a polynomial has. Then we also need to understand what end behavior is. We will delve into this more tomorrow, but for now, end behavior deals with what direction the arrows of the graph are going. So today is going to be just a very basic understanding of end behavior. What way do the arrows go? And we'll make it more formal and more Algebra 2 level next time. So what we're going to do is we're going to be given a graph of 2x plus 3. I know a lot of you know what 2x plus 3 looks like, but I want to be consistent and I want to sketch the graph on our calculator. Then we're going to answer some questions about it. So what we're going to be doing here is you will sketch the graph 2x plus 3 on your calculator, and you see that it's a linear function with a positive slope, positive y-intercept. Now we're going to sketch that graph on our paper. So it doesn't have to be perfect. We just know that this has the same shape, positive y-intercept, positive slope. Now let's talk about the equation and the graph here. The first line says degree. Now I said just before the degree is the highest exponent that a polynomial has. So I look at the x value, that's where the exponent comes from here, and since it's just a regular x, that has an exponent of 1. 1 is actually the degree because that's the highest exponent that a variable has. This graph is a line, so it has 0 turns. When I talk about X-Intercepts, this graph has 1 of them. Now the EB stands for end behavior in this investigation. End behavior on the left. So where is the arrow on the left side of the graph going? And that arrow is going down. So we're just going to be using the words down and up for this investigation. The end behavior on the right is going up towards positive infinity. Now the next 2 questions are circle yes or no. They want to know, is the domain all real numbers? Does the graph go forever in the left x direction and forever in the right? This graph is a yes. The domain is all real numbers because the arrows go out forever. The range is also all real numbers because my graph goes down forever and up forever. Okay. Now you can try the second one on your own, but I'm going to go through the picture with you as well. So I have negative 3x plus 1. So I'll change my equation here and graph it. See, this time I have a line with a negative slope and positive y-intercept. So I'm going to sketch this graph. It'll look something like this on your paper. Now we're going to answer the same questions. This is a linear function again. The degree here, the highest exponent, is a 1. With my graph here that's a line, it doesn't turn. There are 0 turns and direction changes. Again, I look at the x-intercepts. This time there's still only one x-intercept. Now on the left, this time the arrow that's on the left side is going up. So my end behavior on the left is going up, and the end behavior on the right is going down. All right, is the domain all real numbers? Does the graph go forever to the left and forever to the right? That would be a yes. And same with the range. The graph goes up forever and down forever, so the range is also all real numbers. All right, on to number 3 and 4. 3, I have x squared plus 2x minus 5. We'll start by sketching our picture here. Okay, so x squared. And when we hit graph, we see a parabola. So take a minute. I want you to sketch that parabola onto your paper. You can hit pause if you need to. But here is roughly what that parabola looks like. Now this time, let's talk about degree. Degree is the highest exponent that this polynomial has. So when I look here, I have 2 x's. One x has an exponent of 2, the other has an exponent of 1. Well, 2 is bigger than 1, so the degree of this polynomial is 2. The number of turns, how many times does this graph change direction? Well, it looks like I only turn 1 time on this graph. My number of x-intercepts, looks like I crossed the axis twice. Okay, let's talk about M behavior. M behavior on the left. The left arrow here is pointing up, and it also looks like the right arrow is pointing up to positive infinity. Now the domain of this graph, my x's, notice that my graph is going to go left forever and out to the right forever. So that means, yes, my domain is all real numbers. However, the range, I go up forever, but I'm limited. I stop at the bottom. I do not go down forever. So my range is not all real numbers. All right, let's take a look at number 4. Negative x squared plus 6. So I'll type this one into my calculator. And I get a parabola that's upside down this time. So let's go ahead, you can pause the video if you need, to sketch that parabola on your paper. And we look something like this. Now, the degree, again, highest exponent. So when I look at the exponent here, there's only one x, and so its highest exponent is 2. This is a polynomial with degree of 2. The graph turns, changes direction again, only right here, 1 time. And on this graph, there's also 2 x-intercepts. All right, M behavior, the left arrow this time is going down. The arrow on the right here is also going down. Now, just like the parabola that we did in number 3, the domain, this arrow goes out to the left forever and out to the right in the x direction forever. So this domain is, yes, all real numbers. However, like the previous parabola, I can go down forever in this graph, but I can't go up forever. My graph is limited in how high it goes. So the range is not all real numbers. All right, so we've done degree 1, degree 2. Let's move on to some new graphs. 2x cubed minus 7x plus 1. Let's graph this and see what it looks like. So make sure you use the caret when you are, 2x cubed, arrow out of the exponent there, minus 7x plus 1. All right, so when I graph this one, it looks a little different. We're going to talk about what this is called next class, but this is a cool looking graph. Why don't you go ahead and sketch that picture. You can hit pause if you need to. Looks like I squiggle a couple times, and there's my graph. All right, now, the degree of this polynomial. I have 2 x's. The first one has an exponent of 3. The second x has an exponent of 1. The higher exponent is 3. So this is a polynomial with degree 3. The turns. It looks like I turn and change direction once here and once here. So this graph has 2 turns to it. All right, I look at the x-intercepts. 1, 2, 3 of them. So I have 3 x-intercepts. And let's look at the M behavior. The arrow on the left is going down. The arrow on the right is going up. Now my domain. The arrows are, it doesn't look like it, it's hard to tell here, but the arrow is going out to the left forever and out to the right forever. So the domain is, yes, all real numbers. Also, same with the range, because I have an arrow going down and an arrow pointing up, my range is all real numbers. Now when I look at number 6, let's take a look at this graph. Go ahead and type negative x cubed plus 5x plus 2 into your calculator. So negative x cubed, arrow out of the exponent. All right, and when I take a look, it's also a squiggly looking graph. Looks slightly different than the one in the last example though. So let's go ahead and sketch this on our paper. Something like that, similar to that at least. So same kind of squiggles, but looks like the arrows are going in the opposite direction. My degree, highest exponent. I have a 3 and a 1. 3 is higher, so the degree is 3. The number of turns here. I changed direction right here, and I changed direction here. That's 2 times I changed direction, so I have 2 turns. Number of X-intercepts. Again, I cross 1, 2, 3 times. There are 3 X-intercepts. All right, let's talk about the end behavior. On the left, the arrow here is pointing up. So that's the end behavior on the left. The end behavior on the right, this arrow is pointing down. Now, domain and range, same as the last graph actually. My arrows are going left and right slowly, but they're going out to the left and right forever. So this does have a domain that's all real numbers. Also, because my arrow is going up and down in both directions, my range is also all real numbers. All right, we're getting there, almost done. Flip your paper over. My next graph, x to the 4th minus 2x squared plus 3. Let's take a second to graph this and see what it looks like. So I have x to the 4th, arrow out of the exponent, minus 2x squared plus 3. Oh, that's a cool looking graph. That's different than something we've ever seen before. It kind of looks like a W. All right, so let's sketch that one on our paper. So we have something that looks like that a little bit. All right, so let's talk about degree here. Highest exponent. So I have an exponent of 4 and an exponent of 2. The higher one is 4. So this polynomial has degree 4. The turning points. Let's see how many times we turn. Looks like I turn here once, twice, and 3 times. So this polynomial has 3 turns. There are actually 0 X-intercepts on this graph, so I'll put a 0. The end behavior on the left, the arrow is going up on the left, and the arrow is going up on the right. My domain, my x's. Well, the arrow is going out in the left and right direction, both of them forever, so yes, has a domain of all real numbers. However, this time my graph goes up forever, the arrows both point up, but it looks like I stop at the bottom, I don't go down forever, so my range is no. All right, next graph, there's a little bit more to type here, so I want to give you a second to be careful. Negative x to the 4th plus 3x cubed plus 2x squared minus 7x minus 1. So let's take a second to carefully type that in. Make sure you arrow out of the exponents as you go. All right, so that's all there. I think it looks right. We'll hit graph. Oh, that's different as well. So it looks like an M, so it looks like the upside down W, but it does look a little bit different this time. So take a minute, sketch this graph on your paper, and then let's talk about the characteristics. All right, so let's see. So we come up here. Didn't come quite so high. That's close enough. I think that's fairly representative of that picture there. Okay. So our degree, highest exponent. Well, I have a 4, a 3, a 2, and an exponent of 1. The highest exponent is 4, so that's our degree. On this graph, the number of turning points. Well, I turn here, that's 1 time, 2 times, 3 times. So this graph has 3 turns. This time the x-intercepts is different. We have 1, 2, 3, 4 x-intercepts. The end behavior on the left arrow is going down. And over here, the right arrow is also going down. Now we seem to have this pattern. It does look like the arrows are going both out to the left and right forever. So my domain is all real numbers. And for the range, my arrows both are going down, but notice there's a limit to how high you can go. It's not going up forever. So the range is not all real numbers. All right, last 2, and then let's make some connections and tie things together. X to the 5th minus 5x cubed plus 4x. So So let's graph that. We'll get rid of that cool looking graph. X to the 5th minus 5x cubed plus 4x. All right, so I graphed that. Oh, that's even cooler than the last one. Lots of squiggles. Probably didn't even know graphs could look like that. So go ahead and pause the video, copy that graph onto your paper, and we'll talk about it. So let's see, I'm going to try to do it justice here. So come up, down, and up. All right, I think that's kind of close. Yeah, it's not perfect, but it's the same. The squiggles are in the same spot. We're pretty good. All right, so let's talk about degree. Highest exponent, 5, 3, and 1. The highest exponent is 5, so this is a degree of 5. Now the number of turns, I have 1 turn, 2, 3, 4. I actually have 4 turns in this polynomial. X-intercepts, let's see, 1, 2, 3, 4, 5. So 5 X-intercepts. The end behavior on the left arrow is pointing down, and the right arrow is pointing up. Now my domain, x's, just like every other graph, it goes out to the left and to the right forever. So this domain is all real numbers. My range, my arrow is pointing down, and I have an arrow pointing up. So the range is also all real numbers. All right, so last graph here, number 10. Negative x to the 5th plus 5x cubed minus 4x. So let's take a look at what this one looks like. Okay, so negative x to the 5th plus 5x cubed minus 4x. And this one looks same kind of squiggly, but a little bit different. All right, so let's take a minute, pause the video. This will be the last one we have to copy over. So go down. All right, I think that's close. Let's see. Oh, wait, calculator. Yeah, that looks pretty good. So there we go. Last graph. Degree, highest exponent. I have a 5, a 3, and a 1. The highest exponent is 5, so that's our degree. Number of turns again. I will count slowly here. 1, 2, 3, and 4 turns. So my graph turns or changes directions 4 times. The x-intercepts, I count them as 1, 2, 3, 4, 5. This time the end behavior on the left, the arrow is pointing up. The end behavior on the right, the arrow is pointing down. And my domains, well, my arrow on the left is going out forever, and so is the arrow on the right. So my domain is all real numbers. And just like the last graph, I go up and I go down forever. So my range is also all real numbers. So let's summarize this. Let's bring it together. We've seen lots of cool looking graphs here. We figured out what degree looks like, and we figured out that there's a lot of squiggles and turns and some of those main basic features of polynomials. But what does it all mean? Let's kind of put it together. So the question is, what's the relationship between the degree and the number of turns? So let's take a quick look back through. If you think you know, you can write it down, but I'll go through it here with you. Now, if I look at the degree here, my degree in both of these problems was 5. And the graph had 4 turns. All right, let's look at the one before it. The degree was 4, and I had 3 turns. Here the degree was 3, 2 turns on both graphs. All right, degree was 1, and I had 1 turn. All right, so last one, degree of 1 and no turns. So the relationship seems to be that the number of turns looks like it's 1 less, if I flip back through, 1 less than the degree. So we're going to write that down. I hold power to slightly adjust this in a minute. But for now, we'll just say that the number of turns is equal to our degree minus 1, which means 1 less than the degree is the number of terms your polynomial can have. Now, number 2, because we're going to edit number 1 in a minute, says sketch a graph for x to the 4th minus 3. So let's look in our calculator. So let's sketch x to the 4th minus 3. Now when I look at this graph, oh, that one looks different than our other x to the 4th pictures. And I'm going to draw this one real quick, and then we can talk about it. So this graph kind of looks like a parabola there with a really wide bottom. Okay? So again, when I go back to x to the 4th, the degree 4 polynomials, these were the ones that looked like w's and m's. They had lots of squiggles and lots of terms. And the question here is, okay, state the degree. Well, my degree is my highest exponent, so my degree is 1. But this graph looks like it only turns direction 1 time, which is different from the other 4th degree graphs, because these 4th degree graphs both change directions 3 times. So let's take a look here. So this is different because the other 4th degree graphs had 3. I'm going to abbreviate turning points as TP, turning points. Okay, so let's take a second. Let's go back to number 1. It says, what's the relationship between the degree and the number of terms? Well, from our investigation, it looked like the number of terms was just 1 less than the degree. But actually, to modify that, we need to say that the maximum number of terms that a graph can have is the degree minus 1. Because it looks like, from our picture number 2, my graph is allowed to have less than that degree minus 1 terms. So a degree 4 polynomial could have 3 terms or less. Okay, and we'll talk more about that tomorrow. All right, what's similar about the even degree functions? 3, 4, 7, and 8. Well, I'll notice a couple things for you here. 3 and 4, what's similar? Well, it looks like both of their arrows are always pointing in the same direction. So number 3, both arrows are pointing up. Number 4, both arrows are pointing down. Let's see if that's the same for 7 and 8. And it is. On 7, both arrows point up, and 8, both arrows point down. So that's the first one. I would say the arrows either both point up or down. So the arrows both point in the same direction. Let's go back here. Looks like for both of them, the domain is all real numbers, but the range is not. These graphs had a highest point and a lowest point. So the domain is all real numbers here, the range is not. And same on 7 and 8. The domain is all real numbers, the range was limited again, so it's not. So let's put that into words. So we can say the domain is, and I'm going to abbreviate here with the boldface R for all real numbers. We'll say the range is not all real numbers. All right, so the range is limited. And finally, what is similar about the odd degree functions? 1, 2, 5, 6, 9, 10. Okay. So 1, 2, whoops. Oh, where do we go? Here we go. There we are. So what's similar? Well, let's talk about the arrows again. These ones, 1 and 2, look like the arrows have one going down and one going up. 5 and 6 also have an arrow going down and an arrow going up. And the last 2 also have an arrow going down and an arrow going up. So it looks like when I have an odd degree, I have 1 arrows that point in the opposite direction. Alright, so let's talk about the domain and range here. I'll go backwards here. It looks like the domain and the range in 9 and 10 are both all real numbers. Same on 5 and 6. My domain and range are both all real numbers again. So it looks like when I have arrows pointing in both directions, my domain and range are both all real numbers. So the domain and the range are all real numbers. All right, now I missed a question here, so I'll write it in. Question 5 is asking about what's the relationship between the x-intercepts and the degree. All right, how are they related to each other? Well, let's go back real quick. It looks like if I compare the x-intercepts, my degree in this one was 5, the x-intercepts was 5. The degree is 5, the x-intercepts is 5. All right, so it looks like the number of x-intercepts here was the same as the degree. So let's look at another graph. Here, when I have degree 4, this graph had 0 x-intercepts, but the graph on the right had 4 x-intercepts. The graph with degree 3 had 3 x-intercepts, both of them. And same here for degree of 2. So it looks like that my degree, my x-intercepts, for almost all of them were exactly the same as the degree, except for this graph here in number 7, where it was less than the degree. But it turns out what we can say is that the number of x-intercepts, or I'm sorry, we'll say the maximum number of x-intercepts is equal to the degree. Alright, so that's your video for the first investigation for this unit. If you have questions, go ahead and ask your teacher first.